What does it mean when the universe refuses to behave? Not in the loud way of disaster, but in the quieter way of a number that does not fit, a signal that arrives too early, a structure too vast to belong to the map that created it. For centuries, we have looked upward, believing that the sky, if studied with enough patience, would eventually explain itself. We built lenses, mirrors, radio dishes, orbiting observatories. We learned to read starlight like handwriting and measure distance through flickers that began before human memory had a name. Bit by bit, the cosmos stopped being myth and became evidence. And yet, the deeper our instruments reach, the stranger the evidence becomes. Out there are stars that seem older than time should allow, worlds that circle too close to survive, yet remain, ancient galaxies that appear fully formed when the universe was still in its infancy. There are cold regions that dip below the background warmth of creation itself, in colossal patterns stretching across space so far that our best cosmological rules begin to fray at the edges. Some of these mysteries may one day yield to better math, sharper data, or more patient minds. That has happened before. Science is, in part, the art of being corrected by reality. But correction is not failure. It is how understanding grows. Every impossible object is also an invitation to question the model, to refine the story, to remember that certainty has always been the briefest chapter in human knowledge. This journey is not really about cosmic anomalies alone. It is about us, about the fragile species on a small planet trying to describe a universe that existed long before our first language and will likely continue long after our last. What we call impossible is often just the place where imagination meets its next horizon. And so we begin there, at the edge of what should be true, listening for what the universe might be trying to tell us. What if the oldest light in the universe has a cold scar no one fully expected? Imagine a map not of nations or oceans, but of afterglow. A faint bath of radiation stretches across the sky, the leftover warmth of the Big Bang, still drifting through space like the final note of an ancient song. To astronomers, this cosmic microwave background is more than a relic. It is a portrait of the universe when it was very young, a time before stars, before galaxies, before anything familiar had taken shape. Most of that portrait is remarkably even. Tiny variations exist, as they should, because those subtle differences would one day become clusters of galaxies and empty cosmic planes. But within that near-uniform glow, researchers found something unsettling. A vast region noticeably colder than its surroundings. A patch so large and unusual that it felt less like texture and more like a question. It came to be known as the cold spot. At first, the discovery seemed like the kind of irregularity science learns to tame. Perhaps it was a statistical fluke, an accident of scale. Perhaps light had passed through an enormous cosmic void, losing energy as it crossed a region nearly empty of matter. That explanation carried a certain elegance. Space itself, stretched thin enough, could leave a bruise on ancient light. But the evidence never settled as neatly as many hoped. The void appeared insufficient to explain the full depth of the anomaly. Other ideas emerged, more speculative and more difficult to prove. Was it simply an extreme coincidence? A sign that our models of the early universe are incomplete? A whisper from some larger structure beyond the observable horizon? Most scientists remain cautious, and rightly so. The cold spot is not proof of exotic new physics. It is, for now, a puzzle still waiting for its most honest answer. And maybe that is why it lingers in the imagination, because the cold spot is more than a colder patch on a scientific map. It reminds us that even the universe's earliest memory may contain shadows we do not yet know how to read. We like to think that the beginning left behind a clear message. But what if some parts of that message arrive smudged, interrupted, or written in a language we have not fully learned to hear? In the silence between measurement and meaning, curiosity survives, and sometimes that is where discovery truly begins. How can a galaxy look mature when the universe itself was still learning how to exist? Picture the early cosmos as a dark shoreline before dawn. Matter is gathering. Gravity is beginning its patient work. The first stars are expected to flicker into being slowly, almost tentatively, as if the universe must first discover how to build before it can create anything grand. That has long been the broad outline of the story. Small structures first, larger ones later, order arriving step by step across immense time. Then our telescopes began looking farther back. Because distance in space is also distance in time, the deepest observations are a form of archaeology. We are not seeing galaxies as they are. We are seeing them as they were billions of years ago when the cosmos was very young. And in that ancient light, astronomers have found something unsettling. Galaxies that already seem surprisingly bright, massive and organized, appearing far earlier than many models anticipated. They are not impossible in the strict sense. Nature rarely announces impossibility so clearly, but they are uncomfortably early, as if entire cities had appeared in history before the invention of roads. Stars seem to have formed fast, structure seems to have assembled quickly. In some cases, black holes at galactic centers also appear to have grown with astonishing speed, adding to the feeling that the universe may have been more efficient or more chaotic than expected. This does not mean cosmology has failed. More likely, it means the first chapters were richer than our simplified diagrams allowed. Maybe gas cooled faster in certain conditions. Maybe star formation came in violent bursts. Maybe the young universe was not a gentle rise into complexity, but a place of sudden accelerations, where matter rushed into form with a confidence we are only beginning to understand. There is something deeply human in this kind of revision. We tell ourselves that growth should be gradual, orderly, earned through visible stages. Then reality offers another pattern. A child speaks sooner than expected. A civilization changes in a generation. A galaxy blooms before the clock seems ready. And so these early structures do more than challenge timing charts. They ask whether our assumptions about becoming are too narrow. Perhaps the universe did not stumble into complexity. Perhaps from the beginning it carried a hidden talent for emergence, a way of leaping ahead while we were still writing the rules. To look at those ancient galaxies is to witness maturity arriving in the half-light of creation. Not fully explained, not fully denied. Just there, shining across billions of years, asking whether the cosmos has always been older in spirit than we imagined. What kind of star seems to remember a time before it should have existed at all? In the dark halo of our own galaxy, far from the bright, crowded disk where younger stars are born, there are ancient suns still burning with extraordinary patience. They are dimmer than the stars that dominate the night sky, quieter in appearance, easy to overlook. Yet some of them may be among the oldest surviving objects we have ever studied, living archives from the earliest eras of the cosmos. One star in particular unsettled astronomers because its estimated age appeared to press dangerously close to the age of the universe itself. For a moment, the arithmetic felt upside down. How could a star be almost as old as everything? Had the measurements gone wrong? Were the models incomplete? Or had this small point of light exposed a weakness in the way we reconstruct cosmic history? To estimate the age of such a star is an act of layered inference. Researchers study its brightness, its chemical composition, its distance, its internal structure. They compare observation with theory, using stellar evolution as a clock. But clocks built from nature are not as simple as those on a wall. Change one assumption about composition or temperature, and the story shifts. Improve the distance measurement, and the years may soften. What first appears impossible can become merely uncertain, which is often how science regains its footing. Still, the tension matters. These ancient stars contain very little of the heavier elements forged by generations of stellar death. They were born when the universe was still chemically young, before carbon, oxygen, iron, and the other ingredients of planets and bodies had become common. In them, astronomers glimpse a cleaner era, a cosmos not yet enriched by its own history. They are survivors from a time when the sky would have looked unfamiliar even to imagination. There is a quiet beauty in that. A star can endure for billions of years, holding within it evidence of beginnings no human eye could witness. It burns not as a monument, but as a process. Fusion, balance, gravity, time. And by studying it, we are reminded that the oldest things are not always the largest or loudest. Sometimes they are faint, remote, and almost lost in the dark. Perhaps that is why such stars move us. They are not just data points with error bars. They are examples of persistence on a scale that humbles every human schedule. In their light is a simple and unsettling thought. The universe may still contain witnesses to its first age, and we are only now learning how to listen to what they remember. Could a planet survive where reason says it should be undone? Close to certain stars, there are worlds that seem to live in the wrong neighborhood. They are enormous, often the size of Jupiter or larger, yet they orbit so near their suns that a year can pass in days. Their skies, if skies can still be imagined there, are blasted by radiation. Their atmospheres are heated to extremes that stretch the language of weather beyond anything familiar on Earth. These are the so-called hot Jupiters, and when they were first discovered, they disrupted one of astronomy's quiet expectations. For a long time, our solar system had been the model we knew best. Rocky planets live near the sun. Giant gas planets form farther out, where ice and cold allowed them to gather mass slowly and hold on to vast envelopes of hydrogen and helium. It seemed orderly, sensible, almost architectural. Then the exoplanet data arrived and revealed a cosmos less interested in our neat arrangements. Some giant planets were found skimming their stars at distances once thought implausible. They should not have formed there, at least not according to traditional models. The environment would have been too hot, too turbulent, too star-drenched for such worlds to assemble in place. So astronomers began considering another possibility. Perhaps these planets were born farther away and migrated inward over time, pulled by gravitational interactions, collisions, or the slow drag of the disks that formed them. That idea helped, but it also opened a larger truth. Planetary systems may be restless places. Orbits shift, giants wander. Smaller worlds may be scattered, consumed, or thrown into darkness. What looks stable from a distance may in fact be the aftermath of ancient upheaval. There is something haunting in that image. A planet larger than any in our own system, circling so close to its star that its upper atmosphere may stream away into space as if the world is gradually dissolving under the light that defines it. It is both majestic and fragile, a reminder that endurance does not always look like safety. Sometimes survival means existing in conditions that seem almost incompatible with continuation. These worlds matter because they changed more than planetary science. They changed our sense of normal. They taught us that the universe is under no obligation to build solar systems in the image of our own. And perhaps that lesson extends beyond astronomy. We often mistake familiarity for law, assuming that what we know is what must be. Then reality presents another arrangement, harsher, stranger, yet fully real. A hot Jupiter circling too close to its star is not a violation of nature. It is a correction of our imagination. And in that correction lies a deeper invitation, to accept that creation is often messier, more inventive, and more resilient than our first models allow. What if the largest structures in the universe are too large for the universe we thought we understood? Stand in an open field at night, and the stars seem scattered, almost random, like grains of light thrown across black glass. But on the grandest scales, the cosmos is not random at all. Galaxies gather into clusters. Clusters link into filaments. Between them stretch immense voids, vast regions where matter thins into near emptiness. Taken together, the universe resembles a kind of cosmic web, delicate in concept, enormous in reality. For decades, cosmologists believed they understood the rough limits of this pattern. Given the age of the universe and the speed at which matter could clump under gravity, structures should only grow so large before statistical expectation gives way to improbability. The web could be immense, yes, but not without boundary. Then astronomers began finding arrangements that seemed to push against those boundaries. Giant arcs of galaxies, superclusters, enormous walls of matter spanning distances so great they felt less like objects and more like interruptions in the logic of scale. These discoveries remain debated in detail. Some may reflect how we define a structure. Some may be amplified by the way we observe from one corner of the universe rather than from nowhere at all. A pattern can seem more coherent when seen through limited perspective, and yet the unease persists. Even cautious interpretations admit the same underlying tension. The universe may organize itself over distances that strain our assumptions about uniformity. This matters because modern cosmology rests on a principle both elegant and humbling. On very large scales, the universe is assumed to be broadly the same everywhere, without a preferred center or direction. That idea has served science well. It allows us to model cosmic history with remarkable success. But when structures begin to look too expansive, too connected, too improbable, the principle is not shattered. It is tested. There is something deeply familiar in that tension. Human beings depend on patterns to navigate the world. We need frameworks. We build them in science, in memory, in culture, in the stories we tell about how life should unfold. Most of the time, those frameworks hold. Then something appears at the edge of experience that does not quite fit. Not enough to destroy the model, but enough to remind us that reality is always larger than the map. These cosmic giants do not necessarily rewrite the laws of the universe, but they do restore a certain humility to our certainty. They suggest that scale itself can mislead us, that even in a cosmos described by equations, there may still be room for astonishment. And perhaps that is the quiet lesson hidden in these vast formations, that order is real but never final, and that every horizon we draw may simply be the beginning of a larger design we have not yet learned to see. How does a black hole become enormous before the universe has had time to grow old? There are moments in astronomy when distance stops feeling like measurement and starts feeling like memory. When we look deep into space, we are seeing ancient light, messages sent long before Earth formed its oceans or trees or names. Among the most startling of those messages are quasars, brilliant beacons from the early universe, powered by black holes so massive that they outshine entire galaxies. That brightness is the clue in the problem. To produce such intensity, a black hole must be feeding on matter at an extraordinary rate. Gas spirals inward, heats to ferocious temperatures, and releases energy before crossing the point of no return. But some of the earliest quasars we have detected already contain black holes with masses measured in hundreds of millions or even billions of suns, appearing when the cosmos was still very young. According to simpler growth models, there should hardly have been enough time to build them. So astronomers began asking harder questions. Maybe the first black holes were born larger than expected, not from ordinary stellar collapse, but from the direct collapse of massive primordial clouds. Maybe they fed almost continuously, with few interruptions, growing in dense young galaxies where fuel was abundant. Maybe mergers helped accelerate the process. Or maybe our models of early structure formation still underestimate how quickly gravity can gather matter under the right conditions. None of these ideas is pure fantasy. Each is grounded in physics, though none solves every tension cleanly. That is what makes these objects so compelling. They are not violations of knowledge. They are stress tests for it. And beyond the equations, there is something almost poetic in their existence. In the first age of starlight, when the universe was still assembling its earliest forms, there were already regions of such appetite and gravity that space itself bent toward silence. Black holes are often described as endings, places where matter vanishes from view. Yet in quasars, they also become creators of visibility, engines so powerful that they illuminate the darkness around them. Perhaps that is why they stay with us. They embody a paradox we recognize in other forms of life, that what seems empty can shape everything nearby, that absence can become influence, that unseen centers often organize the visible world. These early giants remind us that the young universe may not have been gentle or slow. It may have been a place of sudden concentration, where matter rushed toward depth before we expected depth to exist. And if that is true, then perhaps creation has always contained this strange duality. Light born at the edge of darkness, and understanding born where our timelines begin to fail. Can a place in space be colder than the echo of creation itself? At first, that sounds like a contradiction. The universe is filled with a faint baseline temperature, the cosmic microwave background, the lingering warmth of the Big Bang spread across all directions like a nearly uniform whisper. Nothing should easily slip beneath that ancient floor. And yet, in a distant region of space, astronomers found a place that appears to do exactly that. It is known as the Boomerang Nebula. Seen through a telescope, it does not announce its strangeness immediately. It is beautiful in the quiet way many nebulae are beautiful, a shaped cloud of Gaussian dust cast into the dark. But hidden within that form is a remarkable physical process. A dying star at its center is shedding material outward at extraordinary speed. As the gas expands, it cools dramatically, much the way air rushing from a pressurized container grows cold. In this case, the cooling is so extreme that parts of the nebula seem to drop below the temperature of the cosmic background itself. For scientists, the explanation is not mystical. It is rooted in thermodynamics, pressure, expansion, and stellar evolution. The universe has not broken its own rules. Rather, it has used them with unusual elegance. Under the right conditions, a star nearing the end of its life can create an environment more frigid than the oldest radiation in space. What sounds impossible becomes an example of nature being more inventive than intuition. Still, the emotional power of the image remains. There is something haunting about a star's final chapters producing not only light and motion, but one of the coldest known places in the cosmos. We tend to imagine death in astronomy as fire, explosion, collapse, brightness. But here the story turns in another direction. The star's fading becomes an act of cooling, an exhalation so intense that it leaves behind a pocket of profound cold, almost like a silence made visible. And perhaps that is the deeper reason this nebula stays with us. It reveals that endings are not always loud. Some transformations do not arrive as violence. They arrive as dispersal, as thinning, as a gradual surrender into stillness. The universe, even in decay, continues to create forms that surprise us. The Boomerang Nebula asks for a different kind of imagination. It reminds us that emptiness can have texture, that cold can tell a story, and that even near the end of a star's life, nature can compose something both precise and deeply strange. In that frozen breath drifting across space, we encounter a humbling truth. The cosmos is never less creative than when we think we already understand its limits. What if space itself can sing, and what we hear is the aftermath of something almost impossible? For most of human history, the universe reached us through light. Stars glittered, planets wandered, galaxies glowed faintly across the black. But light is only one language the cosmos speaks. There is another, quieter and more difficult to catch. Gravity, the subtle shaping of space and time by mass and motion. For generations, it was a prediction on paper. Then, at last, it became a signal. When gravitational waves were first detected, they arrived as a minute distortion, a ripple so small it altered measurement by less than the width of an atomic nucleus. Yet hidden inside that delicate motion was an event of unimaginable scale. Two black holes spiraling inward, colliding, emerging far from Earth. The instruments did not see the event. They felt it, like a tremor passing through the fabric of reality itself. That alone would have been extraordinary. But some of the mergers that followed carried a deeper mystery. Certain black holes appeared to fall into a mass range that earlier stellar models had treated with caution, even suggesting that black holes of those sizes should be difficult, or in some cases impossible, to form directly from dying stars. The details are technical, shaped by how massive stars lose material and how pair instability can disrupt them before collapse. But the emotional truth is simpler. Nature was once again producing objects that sat in the gaps of our expectations. How did they form? Perhaps through earlier mergers, black holes built from previous collisions, growing in crowded stellar environments like ancient cities built atop older ruins. Perhaps our understanding of stellar death is incomplete. Perhaps both are true. As always, the anomaly does not erase physics. It asks physics to become more complete. There is something deeply moving in that progression. We once imagined the universe as silent because our senses were too narrow to hear it. Then we built instruments delicate enough to detect a passing wrinkle in space-time and discovered not silence, but resonance. Catastrophe became music of a kind, not metaphorically alone, but in the literal language of waves, frequency, amplitude, and decay. And in those brief signals lasting fractions of a second, whole stories are compressed. Objects born from ancient stars spend eons falling toward one another, then merge in an instant, releasing energy on a scale beyond ordinary comprehension. We receive the echo long afterward on a small planet orbiting an ordinary star, and somehow understand that the universe has spoken. Maybe that is the lesson hidden inside these unlikely collisions. Reality is not only stranger than we expected, it is also more audible, more expressive, more alive with pattern. The cosmos does not merely shine, it trembles. And when it does, it reminds us that even the darkest objects can leave behind a kind of song. What if an entire planet can disappear? Not because it is gone, but because it is hiding in plain sight. For a long time, astronomers assumed planets would reveal themselves in familiar ways. They might dim a star as they passed in front of it. They might tug gently on its motion, causing the star to wobble. They might reflect light or radiate heat. Detection, though difficult, followed a logic. Find the effect, infer the world. But the deeper we looked, the more the universe offered objects that seemed determined to resist clean categories. Among the strangest are the so-called rogue planets, worlds that drift through space without orbiting any star at all. They are not anchored to a warm center. They travel through the dark alone, likely flung outward by gravitational turmoil in their birth systems, or perhaps formed in isolation from collapsing clouds of gas. In older models of planetary order, such worlds felt almost like leftovers, exceptions produced by cosmic disorder. Now they seem less rare and more revealing. Their existence changes the emotional architecture of what a planet can be. We grow up with an image of worlds as dependents of stars. A solar system appears like a family, each planet bound to a central light, held in place by gravity and time. Rogue planets break that image. They suggest that some worlds spend their lives in deep interstellar night, without sunrise, without the steady geometry of seasons, without a sunlit sky at all. And yet they remain worlds, with mass, atmosphere perhaps, weather perhaps, moons perhaps, and histories shaped by forces we can only partly reconstruct. This does not mean they are impossible by the laws of physics. Far from it. Gravitational scattering can be violent. Young planetary systems may be unstable, crowded with giant worlds whose migrations throw smaller bodies outward like stones from a sling. What once seemed improbable now looks like a natural consequence of restless beginnings. Still, there is a lingering strangeness in realizing that the galaxy may be full of orphaned planets wandering between the stars. That image carries a surprisingly human weight. We are drawn to belonging, to systems, to the assurance that everything meaningful must circle something brighter than itself. Rogue planets challenge that instinct. They exist without the framework we assumed was necessary. They move through cold, unlit distances and remain part of the universe's story all the same. Perhaps that is why they feel so haunting. They remind us that not everything in creation is centered, sheltered, or easily seen. Some things endure in separation. Some histories continue after ejection. In some worlds, though hidden from warmth and almost invisible to ordinary methods, still travel onward through the dark, carrying their silent evidence that existence does not always require a home we can recognize. What if a star could die and then seem to die again? The sky teaches us to think of endings as singular. A star exhausts its fuel, collapses, explodes, fades. The sequence feels almost ceremonial, as if the universe respects a clear final act. Yet some observations suggest that nature is not always so tidy. In rare cases, astronomers have seen stellar outbursts that look like death, only to find that the story was not over. These events are sometimes called supernova imposters, eruptions so luminous they can resemble the destruction of a star without fully completing it. A massive star can cast off huge amounts of material, brightening dramatically and shedding its outer layers in violent convulsions. From a distance, it may appear to have reached its final moment. Then, months or years later, another eruption comes, or the true supernova follows, as if the star had been rehearsing its own disappearance. For researchers, such behavior is a reminder of how incomplete our understanding of stellar death can still be. The final years of very massive stars may involve instability, pulses, collisions with previously ejected material, and internal processes that remain difficult to model. The star does not simply cross a finish line. It may stagger, flare, recover, and collapse only after a series of unresolved crises. The neat diagram gives way to something more biological, more erratic, almost more intimate. There is a strange emotional force in that uncertainty. We often speak of stars as distant machines, governed by pressure, fusion, and gravity. All of that is true. But when a star erupts more than once, when it appears to hesitate at the threshold of extinction, it begins to feel less like a mechanism and more like a drama unfolding across time. Not because it possesses intention, but because our own minds are built to recognize tension in anything that resists closure. And perhaps that is the deeper resonance of these deceptive endings. Human lives, too, are rarely defined by one clean turning point. Illness comes and recedes. Empires decline in stages. Relationships end long before they are named as ended. We look for the single moment that explains everything, then discover that reality prefers layers. These unstable stars challenge the elegance of finality. They suggest that endings may have preludes, echoes, and false alarms. Even in the realm of astrophysics, where equations guide the narrative, there remains room for ambiguity. A star can appear to cross into absence and still hold something in reserve. In that hesitation, there is a quiet truth. The universe does not always separate becoming and ending with a sharp line. Sometimes it blurs them together, asking us to watch more carefully. Sometimes what looks like the end is only a brighter chapter in a process still unfolding in the dark. What if the most revealing thing in space is something we cannot see at all? Look at the night sky, and it is easy to believe that light tells the whole story. Stars define the constellations. Galaxies mark the deep field. Nebulae bloom in color where gas catches radiation and gives it back. Yet for all this visible grandeur, astronomers now understand that the matter we can detect directly may be only a fraction of what is truly there. The universe behaves as though it is filled with an invisible presence, something that exerts gravity, shapes motion, and guides the architecture of cosmic structure without offering light of its own. We call it dark matter, though the name is really a confession of ignorance more than a description. The evidence is indirect but persistent. Galaxies rotate too quickly for their visible mass alone to hold together. Clusters of galaxies bend white more strongly than their luminous matter can explain. The large-scale web of the cosmos appears to have formed with help from an unseen scaffold, a hidden framework whose gravity gathered ordinary matter into stars and galaxies. Again and again, observation points toward the same unsettling conclusion. Much of the universe is missing from view, yet not missing from effect. That is what makes dark matter feel almost philosophical as much as physical. It is not a decorative mystery. It is structural. Without it, many of our models of cosmic evolution would fail to match what we actually observe. And still, after decades of experiments, we do not know exactly what dark matter is. Perhaps it is made of particles not yet detected. Perhaps it points toward a deeper revision of gravity itself in certain regimes. Perhaps the answer lies somewhere between refined theory and patient observation. Science continues to test, eliminate, revise. There is humility in that kind of persistence. We live in a culture that often mistakes visibility for reality. If something cannot be shown, counted easily, or placed before the eye, it is treated as doubtful. But the universe has always been less obedient than that. In astronomy, the unseen leaves fingerprints everywhere. It guides stars, bends light, shapes motion, and builds the largest known patterns in existence without ever stepping into the spotlight. Maybe that is why dark matter captures the imagination so deeply. It reminds us that absence is not the same as nothingness. What cannot be touched directly may still define the world around it. The invisible may be foundational, not marginal. And so this great cosmic mystery remains. Not a ghost story, not a myth, but a measured encounter with the limits of perception. The heavens are filled with light, yes, but perhaps their deeper truth lies in what the light is forced to circle, obey, and reveal only by consequence. What if the deepest mystery in the universe is not what exists, but why so much of it is moving away faster than expected? For much of modern astronomy, the story of cosmic expansion seemed clear enough. Since the universe began in a hot, dense state, space itself has been stretching ever since, carrying galaxies apart like flecks on the surface of an inflating sphere. Gravity, meanwhile, should act as a kind of restraint, slowing that expansion over time, however gradually, by the mutual pull of all matter on all matter. Then came one of the most astonishing reversals in scientific history. By studying distant stellar explosions known as Type Ia supernovae, astronomers realized that the universe was not merely expanding, it was accelerating. Galaxies were receding from one another faster and faster, as if some vast, invisible influence were working against gravity on the largest possible scales. The discovery did not arrive as fantasy or speculation. It came through careful observation, repeated analysis, and the uncomfortable recognition that the cosmos was doing something profoundly counterintuitive. That influence was given a name, dark energy, but the name explains very little. It is a placeholder, a label for the unknown cause of acceleration. It may be a property of empty space itself, a vacuum energy woven into the fabric of the universe. It may reflect a flaw or incompleteness in our understanding of gravity over immense distances. It may point toward a deeper framework not yet fully imagined. At present, the mathematics can describe its effects better than our concepts can describe its nature, and still the implications are enormous. If dark matter helps hold the cosmic web together, dark energy seems to work in the opposite direction, widening the distances between structures over time. It is as if the universe contains both the instinct to gather and the instinct to drift apart. Creation is not only a matter of gravity and accumulation, it also includes dispersal, expansion, and a future shaped by increasing separation. There is something almost painfully human in that balance. We know the force that binds. We also know the force that carries things beyond reach. Families scatter, languages change, memories lose detail at the edges. Entire eras recede, not because they were unreal, but because time itself expands the distance between us and what once felt close. Perhaps that is why dark energy resonates so deeply beyond the physics. It confronts us with a universe that is not settling into stillness, but into widening space. And yet even here, there is wonder. The fact that we can detect such acceleration at all, from one small world around one ordinary star, is a triumph of attention. We have measured the drift of galaxies across billions of light years and found, hidden in that vastness, a question that touches the foundation of everything. The universe is not only stranger than expected, it may be propelled by a mystery built into emptiness itself. And as we follow that mystery outward, we are forced to consider that the future of the cosmos may depend less on what fills space than on what space in its silent nature has been carrying all along. So where does all of this leave us after the cold scars in ancient light, the overgrown galaxies of the early cosmos, the stars that seem to remember the beginning, the wandering planets, the giant structures, the hidden matter, and the force that keeps widening the dark? It leaves us, perhaps, where every honest encounter with the universe eventually leads, not to final answers, but to a more disciplined form of wonder. Science is often imagined as the opposite of mystery, as though each discovery drains the world of awe and replaces it with mechanism. But the opposite is usually true. The better we understand reality, the more subtle and astonishing it becomes. What once seemed simple turns out to be layered. What once seemed settled opens again. A strange object, an unexpected signal, a mismatch between prediction and observation. These are not failures of knowledge. They are the moments when knowledge becomes alive. That may be the quiet thread connecting every anomaly we have followed. None of them asks us to abandon reason. None requires myth in place of method. Instead, they remind us that reason itself depends on humility. We build models to approach truth, but truth is never obligated to arrive in the shape we prefer. The universe is not a machine built for our comfort. It is older, wider, subtler, and more inventive than the language we bring to it. And yet we keep looking. That's maybe the most moving fact of all. On a small planet, in a thin atmosphere among brief lives and unfinished histories, a species emerged that learned to question the sky. We developed instruments capable of catching light from the dawn of time and waves from colliding black holes. We found evidence of things invisible, distances almost beyond meaning, and patterns so vast they challenged the mind that conceived them. In doing so, we did not become masters of the cosmos. We became better witnesses. Perhaps that is enough. Perhaps the purpose of these mysteries is not to make us feel small, though they do. Perhaps it is to make us feel connected to a reality still unfolding, one in which uncertainty is not a void but an opening. The unanswered question is not the end of understanding. It is the beginning of attention. And so the story closes where it began. at the threshold between what should be and what is. The universe continues to exceed us, and that is not a tragedy. It is a gift. Because as long as there remain things that should not be possible, there will remain something profoundly human in the act of trying to understand them.